Stanley, Winston, John, and Zach.
So hello, welcome. So our project is called Flowdration, and just a brief outline. So basically the most important things to pay attention to would be for our how our project would impact our society, general, obviously the hardware, the software, how it would operate, and the data from this, and the general summary. So for our team, we have Stanley, who is the project leader. We have me, Zach, who is the lead hardware. We have Vincent, who is lead software, and we have John, who is co-lead software.
So this is our motivation for the project. During personal hiking and backpacking excursions, many types of issues are encountered. One issue that arises is the inability to keep track of water supply. With the hydration pack being stuffed into the bag, it wouldn't be so easy to take out and check water content. Constantly being worried about the amount of water left in your reservoir or trying to figure out how often to drink to stay hydrated can be a hassle. It's very easy to become dehydrated during these long trips, especially if it is difficult to monitor water intake. This struggle inspired Flowdration. Accurately keeping track of water consumption and current water level will dramatically improve these experiences. So this is just the project description and the impact it has on society. A major issue that occurs during long, distant, exertive trips is dehydration. Without our product, the user is able to monitor their water intake. With a synced app on the phone, consumers are able to enter new water values and see their current water quantity. The helpful LCD screen shows the user's current water amount and percent that is left from the starting quantity. So bicyclists and runners, hikers, whoever are able to see their current values without stopping and checking. And backpackers will no longer need to empty their bags to check on their water. Also, military personnel will be able to ration and track with ease. So the contribution, why our product is original and unique. So we've improved the accuracy compared to past attempts of similar hydration measuring devices. We have Bluetooth connectivity that allows for ease of use. The application on our phone is not needed during the excursions since we have the LCD screen for monitoring. We have adjustable brightness levels for battery saver modes for long trips, and we have real-time feedback.
So some of the standards that we try to keep in mind for our project was first off the IEEE Bluetooth standard, because our device is trying to run off Bluetooth. So with the IEEE Bluetooth standard, we try to go into the MAC address for security and your physical layer specifications that you have to have for the Bluetooth modules. And there's required frequencies that you might have to adhere to so that you do not affect other radio frequencies that go through, such as medical devices that need the priority for certain bandwidth that you cannot encroach on. And for another one would be the smart sensor standard. Since we're just using a phone meter that is kind of like a smart sensor, the standard will talk about different ways to avoid errors, and a lot of this touches on calibration and other templates and formats that you have to follow for how you do your calibrations and your conversion rates to allow for future users to be able to easily use your device. So as I stated before, the first IEEE 1451.1 there's a template that they provide for how to perform calibrations and to how to state your conversions within your code or within your manual. This way it allows for people in the future who do want to work on your sensor to actually be able to easily use it and pick up from where you started. And a lot of this will tell you about different units that you have to use, or you have to list out the units that you are using and what are your calibration factors, which is such as for ours, it's like 1380 pulses on our flow meter for 1 liter. So you got to list out those little factors for future users. And for the IEEE standard, our Bluetooth device actually follow this standard, so we just piggyback off of that. But it's to help interfere with, it's to prevent interference and fading so that you don't encroach on, as I said before, like medical devices, when they have to use certain radio frequencies, you don't end up jamming their signals. And this usually operates at, the Bluetooth would usually operate around 2.4 gigahertz bandwidth. So for the hardware of our device, we tried to put in an entire compact prototype to try to keep it for something as a sketch or model in the head of what it's going to look like. As you can see for the first picture, it would have an LCD screen, a couple buttons for user input, and an on-off button. And then when you look at the back, what we tried to do is we try to separate the mechanical portions with the electronic portions so that in case any water failures happen, since we're not all plumbers, any water that just accidentally leaks, it doesn't affect our electronics. So we try to keep most of the mechanical stuff on the outside, such as a valve and a flow meter. What happened with previous versions, the valve, we added an extra valve compared to previous versions, because previous versions will only have a flow meter. What happens is that when you're doing your hikes or other biking or other sports activities, your movement will accidentally actually trigger your sensor. So what happened is that we put a valve and we put a electronic button for it to actually, when you press the valve to actually release water, or allow the user to actually drink the water. This would then allow the device to start recording. This way you can remove some of this error of where when you're running or you're just walking or biking, you end up knocking the sensor a couple times and it'll send out a couple pulses and then adding and causing some kind of inaccuracies. And for the last picture, this is just our full build design that we put on a breadboard. We tried to assemble it on into one complete shell, but we were having a lot of issues with a lot of the wiring, and a lot of stuff was shorting out that we couldn't figure out what was going on, and there was just too many wires that we had to deal with. So we just left a simplified diagram where you see how we have one microcontroller and the LCD screen, and we have buttons littered around.
For the software side of things, we started with making the app. This just allowed us for testing, so when we do code the microcontroller, it will be ready for testing purposes. So in the first picture you can see you have a drop-down menu, well, 2 drop-down menus. It says enter the amount of water in your reservoir. This is all done using Android Studio, which is using Java programming, which actually the first time we all have used it, so there's a little learning experience there. So you have the 2 drop-down menus, which let you put up to 3.9 liters, because the max usually is around like 3.5 liters for CamelBaks that you buy. So we let it put 3.9, so there's a little wiggle room if you have a bigger one. So you send it, you put it in, and you click send, and that will send it directly to the Bluetooth module. And we had some issues actually starting with that, but we'll talk about that later on and how we resolve those issues. But yeah, so we send it, and then that will go to the Bluetooth module, which is programmed through the microcontroller. And then below that, on the first picture still, we have remaining amount of water in liters with an update button next to it. When you click that update button, you will receive how much water is remaining in your reservoir. So while the microcontroller is doing all the calculations and everything, it will also send back, it's not just receiving, it sends back information to the application so you can have all what you need on the phone as well. The next picture is just showing you how we pair the devices. Ours is the HC06 device, which is the first device. So when you start up the application, which you'll see in the demonstration video, you click on which one you want, it connects to it, and it brings you to the first screen actually. And then we use the PIC microcontroller, and for that coding we used NPLabX IDE, That was C language. We had some minor difficulties, but we figured it out pretty well. One of the issues we had was converting bytes into integers, but we found solutions around that, and we're able to successfully have them working together, and the code worked pretty much flawlessly. Here we have our demonstration. For this demonstration, we actually ended up using, as Stanley said, we didn't use we used part of the compact device, but we did have some issues. So you'll see that we're using the actual breadboard, and when we recorded it, we didn't notice right away that it was half of it was upside down. So you're gonna see the LCD screen upside down. We were gonna edit it and make it flip, but we didn't want people to think that we were editing the video to change our results. So this is the raw video. Oh no, that's not. How do I play it? There we go. Yeah, so you go in, we click the app, it brings it up, you click on your paired device, connects, then you have the drop-down menus, where you have use 2.8, so you're able to scroll, click on it, and send. So what that's going to do, it's going to send to the LCD, it's going to register as 2.8, so we send it, because of the way the bytes, because you only send 3 bytes at once, so it receives 2.8, that's good, and then we flip it, it says H2O water level 2.8 liters, 100% water remaining. That shows your percent you could drink. So the way it works is we can only show so much because it's going to take a while to drink for it to actually have an impact. It's going to take forever to drink more than 0.1 liter. So you're just going to see it move down 0.1 liter. And since it's upside down, it's actually 96% because 2.7 is 96% of 2.8. But yeah, but to show them greater impact, it's going to require a lot of time that we really didn't have for a video because we'll be here all day.
So for what, as I was saying before, we had to do calibration data. What happened is that during the preliminary testing of our device, we actually realized that when we were doing the unit test for the flow meter, we were realizing that different speeds that we were drinking from was affecting the data itself. We found a good sweet spot of what we call middle speed, and then we started going down from slow and fast. What happened is that we started realizing that many trials, when we were doing it slowly, like small, like little sips, it wouldn't register that many pulses. And then the same idea with when we did it with very quickly, it would register too many pulses at one time. So even though the manufacturer for the flow meter gave us a set value, which is 1380 pulses per liter, we actually drank up to half a liter because we didn't want to sit there for a whole liter of drinking. So then we saw, this is like a summary of the values that we grabbed. What happened is that we used a variable pump that we were able to adjust the speed. Using the PIC, we were actually able to measure out the speed by using the internal time of the clock of the PIC microcontroller and comparing that to the time between each pulse. We were able to measure out the speed of how fast it was going. So we used a pump to try to keep a consistent speed, and we would adjust that. For slow, it was more towards less than 1 liter per minute. So the operating range that the manufacturer gave was 0.3 liters per minute to about 10 liters per minute. What happens is that for slow, we try to keep it to about 0.5 to about 0.6. There was a little bit of adjustments and we got a little bit of error, but we did that for 15 times of half a liter, and we got an average value of 578 pulses per liter. And we would repeat this for medium and fast. For medium, we used around 5 to 6 liters per minute, and for fast, we try to go for 8 to 9, since we were trying to log out how fast we were going, and the fastest we were able to go was like 8 to 9 liters per minute. So that's where we kind of capped off the fast. And we took the averages and we used that as a calibration factor to try to increase the accuracy as a way to innovate on the previous model. So we would do this for calculating of how the PIC would actually perform the math on how fast the water rate is going, and it would log on how much liters is taken away using these modified calibration factors. So this is just graphs showing it. So as you can see, like the slow ranges, you can see the 690 is where the orange one is, which is what is supposed to get from the manufacturer's settings. But from our slow, you can see how it's all very close to all lower, all less than the manufacturer's value. So we just took an average of our values, and we continue doing this for medium. Here it looks more sporadic, but it's actually a lot more consistent. It's just that the scaling of the graph, thanks Excel, scaling of the graph makes it look very, very drastic, but a lot of it's actually very, very close. And then for fast, for the orange, it's our actuals, and for the blue, it's the expected of 690, and the actuals when we were pumping it really, really fast, a lot of the values were a lot higher.
So thanks to the calculations of those past charts and knowing that 1,380 pulses equals to 1 liter for the flow meter, so using that, that's how we were able to subtract and add, to figure out how much water is left. Knowing 1380 is 1 liter, we were using a conversion from pulses to liters, and that let us do the math. And then when we used the speed, we were able to use a formula that took the speeds and fixed it so it worked out with no matter how fast you were drinking, it would change the pulses because it would tell how fast you were drinking, how many pulses would happen, how fast. So that allowed us to more accurately get what we were looking for. This is what differed us from past attempts. They weren't looking at speeds, they weren't looking at the flow meter possibly activating when you're not drinking. So with the formula of the speeds and the 1380 conversion, we were able to get accurate measures for all different volumes of water. We have 150 milliliters, which is actually, or at least, we have a couple ones that are far apart, but it's actually not that bad. 200 milliliters and 500 milliliters. We're reaching our yellow line, which is our perfect score, and then the other ones are our actual. So we're getting around what we need, and we continue to perfect this as we enhance the code and enhance the formula.
So this is just a general circuit diagram of what our breadboard was trying to display. You have the microcontroller in the middle, the LCD, and it's all connected together, Bluetooth on the bottom, a flow meter on the top, and we have assortment of LEDs. That was quickly scrapped because we were running on time constraints, and then we had multiple switches depending on what user functions we wanted to add later on. And there's an oscillator to help create the internal clocking for the pick so it knows the times. And then this is very important for us so that we have to calibrate it really right for what speed, so that we're able to get the speeds of the flow, because we're using, we were calculating speeds from pulses and the intervals between the pulses in time. And then we just have general power supply and variable controllers for the brightness.
We started with some preliminary designs way back when we made promises that what we were going to do, what we planned on doing. One was a personal hydration plan. We wanted to make it so someone can enter how long their trip's going to be, so you can perfectly plan out each steps. This just didn't happen due to time constraints. We wanted to make sure everything else worked properly, so we really just focused on the flow meter getting its accuracy, which personally was the most important and is the whole point of this project. These hydration plans can be easily added later. It's just a matter of actually taking the extra time to code it. We actually took out some buttons because we were going to make it so you can enter the water amounts from the screen itself, like from the mouthpiece. This way you didn't need the app at all. But we found out for this, again, that could just be easily added. So for this stage, we just decided, for now we'll just stick it, if we're entering through the app, we want to make sure it works, we want to get it done. So we made it so you just put it through the phone and make sure everything works and make sure, again, that accuracy was there. We took out our LED lights. I personally felt like this was a really good decision because when you're walking around, you don't really need those lights blinking off because you're not really going to be focusing on lights, and also you're going to be checking your water when you go to drink it, so you're going to know how much is there, you're going to know how much you drink when you're done, and the LED lights are just going to kill the battery faster. There's no reason, so it's better that they're out now. And as I said before, the hydration plan relates directly to mapping and refill stations. If you're going to refill, you can very easily take out your phone and re-enter how much water you put in total. So as I was talking about before, we had challenges. We had our Bluetooth module send and receive our values. So we really struggled here because it was 3 bytes for sending, and we couldn't exactly get it for us sending our values because we had it we were sending 3.7 decimal values. So it was really hard to convert bytes to integers. So our approach here was actually to turn it to, when you enter 3.8, 2.8, it actually is 28. We send it like that, and then we use formulas. We break it down to 2.8, and we actually use modules a lot because just of how the code works and for the bytes. Our custom hardware, as we talked about before, was very constrained. The wires, it was really getting messed up, so we ended up just using the breadboard with part of it with the switch for the constraint, and that ended up working out. We had a couple LCD malfunctions, several coding issues with the bytes, and of course time-related issues. For our fixes, to fix our Bluetooth, we just, as I said, we converted to the one larger number and then broke it down from there. The hardware, we decided to use the original breadboard for some of it. So we actually burnt our first LCD screen, which was our major issue. We weren't understanding what was going wrong. We spent a lot of time trying to figure out why the LCD wasn't working. Turns out we broke it. So we had to buy a new one, and after doing that, we actually thought we burnt the second one when using the compact design. Turns out that was just a circuit issue. When we plugged it back into the breadboard, we're like, all right, this circuit we messed up somewhere. Let's just try to get this, make sure it's accurate and working correctly. And then, having never worked with Java and MPLabX before, we faced a lot of issues. Learning syntax, so it took many hours just attempting to get things right and get things running, and that was important. And then time constraints, of course, we took out some original ideas.
So these are just some of the skills we enhanced. So we created the app using Android Studio, which we had never done before. We never created an app before, so we learned how to do that. But we never used the Java programming language before, so it was a good experience learning how to code in that. We just enhanced our soldering abilities, learned more about the C language and did more things with it, and we learned more about interrupts, pointers, serial transmissions, and how software and hardware are really integrated.
So just to summarize everything, basically we were able to construct an accurate flow meter that was able to keep track of the water we consumed. By using C language and MPLabX, we took the drinking values and had our microcontroller keep track of how much water was left. This worked hand in hand with our applications to give the user an easy experience. And there are additions that can easily be implemented with more time. This is where our references, the standards, and any questions.
Yes.
Hey guys, can you go back to the slides for the standards?
Yeah.
Okay, it's just the comment, it's not the question. So, because it's common mistake, it's not only just from you guys, it's from like a lot of engineers in the market. IEEE are not industrial standards. So, as you know, IEEE is not profit organization. They have their own standards. You can join any committee saying, I have this direction, left is correct, they put it in the standards, right is correct, they put it in the standards. And after that, we have the industrial standards, like Wi-Fi or Zigbee, those are considered as industrial standards. They built on top of the IEEE standard, they just pick some of these standards and they built the industrial standards. So you find the logo of the Wi-Fi or the Bluetooth. So this means this device can talk to other device which has the same logo. And after that, we have the UL certification or FCC certification. So the IEEE are not, I'm just confirming to you guys because I know you're going to be engineers in the market after few days. IEEE are not industrial standards. Okay? So this is clear. So just try to clarify this before you be engineer in the market after few days. That's it. That's my question. And it's common mistakes, so don't worry. Like everyone, like.
That's it? Cool.